Okay, so good afternoon and welcome everyone to this session of the Lisbon Philosophy of Physics seminars. These events are organized in the context of LANCOG Research Group, which is based at the University of Lisbon. In the past seminars, we have been talking about topics involving interpretation of quantum mechanics, QFT, space-time physics. And today is a real pleasure for me to come back to one of my most beloved topics in the philosophy of physics, which is the interpretation of quantum mechanics. And it is also a personal pleasure to introduce our speaker, Olimpia Lombardi. Olimpia is a philosopher from the University of Buenos Aires. She basically needs no introduction because she contributed a lot to our discipline and also to the philosophy of chemistry. She championed the Modal-Hamiltonian Interpretation of quantum mechanics, and she published her research in the most prestigious journal about philosophy of science, philosophy of physics, and philosophy of chemistry. So without any further ado, Olimpia, I would leave you the stage.
Well, thank you very much for the invitation, Andrea. I'm very happy to introduce this interpretation. Especially, I'm very happy to have a lot of time to talk about the interpretation. Of course, I will not be able to say everything because there are a lot of publications, papers around the topic. But anyway, my intention is, my idea is to give you a clear and global idea of the interpretation today. So, well, I sorry for my English. It's during the last years I didn't travel a lot, so my English is a little bit out of training, say. So be patient with me. Okay, so since I have time, I will organize the talk in three parts. First, I will introduce the interpretation. Then I will talk about the ontology that is very related with interpretation, of course, but it's the ontological part of the interpretation, but it has a kind of, it can be considered alone because that ontology could be applied to other views about quantum mechanics. And the third part is to revisit indistinguishability from the viewpoint of this ontology, because it's a point to take into account independently. So let us begin with interpretation. First, the basic postulate. Then I will talk a little bit about the measurable problem. Then I will talk about the invariance of the interpretation that for me is very, very important, a very, very important point. And finally, I will talk about the difference between the Hilbert space formalism and the algebraic formalism, because this will be the door to open the second part of the talk. So the first part, the basic postulates. Let us begin by recall which are the points in which all models interpretations agree. The interpretation is based on the standard formalism of quantum mechanics, so no different postulates, no different formalism. The interpretation is realist, means that it tries to explain what reality should be if the theory were true. It's not about our believings or our bets, nothing at all. It's about reality. Quantum mechanics is a fundamental theory which must describe also macroscopic objects. There is no macroscopic cut. The quantum state describes a single system, not an ensemble of systems, not in the interpretation of the kind of Valentine interpretation. The quantum state of the system describes its possible properties and their corresponding probabilities, and not its actual properties. And this is the modal import of the interpretation. The Schrödinger equation gives the time evolution of probabilities, not of actual properties. Systems possess actual properties at all times, whether or not a measurement is performed on them. And the quantum measurement is an ordinary physical interaction. There is no collapse. There is not something different or another law for measurement. Well, we know that the Cauchy-Specker theorem proves the impossibility of ascribing definite values to all the observables and preserving the structure of quantum mechanics, the structure of observables. So the realist non-collapse interpretation is committed to select a subset of definite valued observables. Not all the observables can be definite valued, so some of them must be selected. The modal interpretations differ between them in their rule of definite value ascription. We call it actualization rule because it's easier, it's shorter, which picks up from the set of all the observables the subset of definite valued properties, definite valued observables. Well, the traditional modal interpretation, I'm thinking about Cauchy and Dix and the generalization of Dix-Vermas, were designed specifically to solve the measurement problem. And they really were successful for ideal measurements. The particularity is that they rely to the state of the system. I mean, they make the definite valued observables or context to depend on the instantaneous state of the system. The problem was that in a series of articles, those articles by Albert and Lower and Elby in general, showed that those approaches are not successful for non-ideal measurements. When we face with those approaches, non-ideal measurements, they don't pick out the right properties. For the apparatus, that is more serious because this is what we see. This was, I think, explains the decline of the interest in modal interpretations since the end of the 90s. Harvey Brown in a paper, in a paper by Ciagalupi and Emo, and Meir-Emo, Guido and Meir, they quote Harvey Brown saying that this kind of shortcoming of model interpretations, for non-ideal measurements, are a silver bullet for killing model interpretation. And I think that this was very relevant, very influential to decline the interest in model interpretations. However, I would say that the difficulties are not due to the modal nature of the interpretation, but on the fact that the actualization rule they used made the set of definite value observables to depend on the instantaneous state of the system. This is not necessary. This was supposed that this should be that way, but this is not necessary. In fact, Jeffrey Babb notices that. And he said, well, the modal interpretation based on the instantaneous state of the system do not work. So, on the other hand, Bohm mechanics can be considered as a member of the modal family. A member that takes the definite value observables defined by position. Position defines the preferred context, if you want. So it turns out to be the natural alternative to this modal interpretation with those problems. This was the time in which, 1997, Jeffrey Babb was Bohmian, because he found this was the alternative. But they didn't see that position is not the only possibility. Why not a different observables to define the preferred context? Let us call preferred context the set of observables of definite value observables. Why not another observable, not only position? Well, this is the idea of the Modal-Hamiltonian interpretation, in which the Hamiltonian gives the rule, the actualization rule, the rule of definite value adscription. Well, this is the Modal-Hamiltonian interpretation is based on the algebraic formalism, and it has two main postulates. One, the system postulate, a quantum system is a pair OH, where O is a space of self-adjoint operators on a Hilbert space, representing the observables of the system. And H is the time-independent Hamiltonian. So in that space of self-adjoint operators, one is taken as special, and it is the Hamiltonian. And the density operator that belongs to the dual space of O is the initial state of the system and evolves according to the Schrödinger, von Neumann, strictly speaking, because it is a density operator, von Neumann equation. Well, this is what explains what a system is. Now, which is the rule of definite value ascription? From now on, the actualization rule is based on this idea, an idea that comes from Romans, ubi lex not distinguit, nec nos distinguere debemus, where the law does not distinguish, neither ought we to distinguish. So, which is the law, or what is the element, central element of the law? It's the Hamiltonian. So, we only have to distinguish what the Hamiltonian distinguishes, not anything else. So, the actualization rule says that given a quantum system, the preferred context of definite value observables consists of H, of the Hamiltonian, and all the observables commuting with the Hamiltonian and having at least its same symmetries. I mean, if one observable commutes with the Hamiltonian but has more symmetries, it would distinguish between states, situations, values that the Hamiltonian does not distinguish. So the observables of the preferred context must have at least the same symmetries of the Hamiltonian. It is interesting, well, that it's interesting that we will not justify this actualization rule a priori. The actualization rule will be justified because it is successful, I think, to answer the problems of the conceptual problems, interpretational problems of quantum mechanics. So the justification is in a certain sense pragmatic in the context of the interpretation. But what is interesting is that sometimes I introduce this interpretation in audience of chemists or philosophers of chemists, and they ask me why I have to explain what is why this is novel? It's obvious that the Hamiltonian rules actualization, it's obvious to work in the basis of the Hamiltonian. For them, I mean, chemists always work in the basis of the Hamiltonian. So, whereas I have to explain in a audience of philosophers of physics, I have to explain why I will use this actualization rule. In an audience of chemists, I have to explain why this is novel, why this is not obvious. It's very interesting because the audience react in completely different ways. So let us continue. Wait a moment. So let us see the measurement problem. We distinguish between a single measurement, a single process, that is the reading of the pointer's value, and in general, the problem of the measurement problem is related with a single measurement, and the difference with the frequency measurement, when one repeats identical single measurement in order to obtain the values of the coefficients of the state. Because with a single measurement, I cannot say nothing about the state. I obtain with a frequency measurement, I obtain the coefficients of the state in that basis, not in other bases. If I have to reconstruct a complete state, I have to make what we call in our paper a state measurement, change the basis, but I will not take this, I will not discuss this point here. What I will say, and I will say I cannot justify this, I send you to the paper, especially to the first paper, the 2008 paper with Mario Castagnino. There, the things are explained with all detail, but I will say that the Modal-Hamiltonian interpretation explains the definite value of the pointer of the measurement of the measuring apparatus, both in ideal single measurements, when we have perfect correlations, and even in non-ideal single measurements. For instance, the Stern-Gerlach with imperfect correlation or with imperfect collimation of the incoming beam. So this interpretation has no the problem of the non-ideal measurement. But moreover, in the non-ideal case, the interpretation can distinguish between reliable and non-reliable frequency measurement. I mean, not all frequency measurement, when it is non-ideal, and I repeat the single process many times, not all times the measurement, the frequency measurement is reliable. I mean, not all times I can recover the state coefficients. So the interpretation can distinguish the reliable case with and the non-reliable case. And I think that this is something interesting because there are not ideal measurements. I mean, ideal measurements are an idealization, precisely. Normal measurements are always non-ideal. Anyway, the physicists can make successful conclusions, can extract conclusions from measurement, even if the ideal is never attained. So the relevance of distinguishing reliable and non-reliable frequency measurement, I think that it's important, and I think that I never seen it in other interpretations. I never seen other interpretations giving this distinction. Well, I will not explain all this part because it should need talk by itself, but I want to say something about conceiving measurement from a different viewpoint. We are used to think the measurement problem in terms of the von Neumann model, that is, if you want, a formal model. What I want to say here is that if we think in measurement as a physical problem, I mean, we think measurement from a physical viewpoint, we can see it as a symmetry breaking process, a process that introduces a symmetry breaking in the system. Let us go to an example. Let us suppose that we have a free particle. This free particle, in this free particle, the Hamiltonian is symmetric under displacement. So in principle, we don't know in which direction the particle is traveling. So according to our interpretation, we cannot say that these three observables, the three components of the momentum are the three definite values, because we don't know in which direction is traveling the particle is traveling. But for this reason, they are not definite value. What have we do to know the direction of the particle? Well, let us suppose that we want to measure Py. What we do? We put a wall. We put something that interferes in the trajectory of the particle. That is, we introduce a potential. But if we introduce the potential, now the system is not this one. Can you see my little? Can you see the pointer here?
Yeah, yes.
Yeah.
We can see it.
Yes, it's the little hand. This is not now. Now, this is not the Hamiltonian anymore. The Hamiltonian is this one. And now it has a part that clearly breaks the symmetry in Y. So now we can know, we can make Py definite value, but because H is not H anymore, it's H prime, and this is not symmetric in Y anymore. Let us suppose a free particle with spin, which we have here the Hamiltonian. This is symmetric under rotations. And we know that they cannot be definite value, the three components. Even they do not commute, so they cannot be definite value, all the three. So we know that well. What happens if we want to measure, say, SZ? Well, a Stern-Gerlach experiment, we put a magnetic field in that direction, in the direction we want to know, and so we can measure SZ. But in that case, H now is this one that includes the magnetic field. So this part breaks the symmetry in Z. And the same if we know we have the hydrogen-like, the hydrogen atom of any hydrogen-like atom, where we have all these quantum numbers. We see that we have three quantum numbers, N, L, and ML. But H, this Hamiltonian, is symmetric under rotations. So even if ML is a good quantum number, it defines the basis, a basis, not the base, a basis for the atom, LZ is not definite value. With this description, we still don't know in what direction we will measure LZ. So when we want to do that, when we want to measure ML, again, we have to include a magnetic field. And when we include the magnetic field, the Hamiltonian now is this one. Again, it includes the magnetic field. This breaks the symmetry in Z, but moreover, the values of the energy, I mean the energy eigenvalues, the values of energy that are interesting in physics, now here they don't depend on ML. When I include this, they begin to depend on ML because they include a term that depends explicitly on the magnetic field and ML. So this means that now the Hamiltonian is not H anymore, but H prime. And this is very general. If I have a Hamiltonian, let us suppose that I have a Hamiltonian of this form. As you see, the eigenvalues depend only on I and not on J. So it is degenerate, it's symmetric in the index J. And I have another observable that is not degenerate. So its eigenvalues depend on I and J. Yeah. Well, if I assume that A has a definite eigenvalue, that eigenvalue would distinguish among eigenvectors corresponding to a single eigenvalue of the Hamiltonian. That definite value would introduce an arbitrary asymmetry in the system. And this is what we consider that it's not physical, because if we want to see that arbitrary asymmetry, we need to break the symmetry of the system. So, in general, as a conclusion, measurement, when considered from a physical viewpoint, is a process that breaks the symmetry of the Hamiltonian and then turns an otherwise non-definite value observable into a definite value and empirically accessible observables. Because if it is, if in the other case, it's not empirically accessible. Well, this idea of measurement as a symmetry breaking process was applied successfully to several physical models. Free particle without spin, as we said, free particle with spin, harmonic oscillator, free hydrogen atom, an atom, to the Zeeman effect to the atom, to find structure in an approximate way to the Born-Oppenheimer approximation, because the Born-Oppenheimer approximation is an approximation. It was very, very interesting, the application to optical isomerism. That is a problem that is pretty unknown by philosophers of physics, but it's central in the philosophy of chemistry. And it was also applied to the case of consecutive measurements. Well, not all the applications are in the same paper, but well, then you can find in the literature, in the reference at the end of the talk, the different applications. Well, what happened with the invariance of the interpretation? A point that for me is very important, I said. In a paper not very well known, I think, of 98, Brown, Suarez, and Bacigalupi say, I think that rightly, very, very, I think that they make a very important point, they say that any interpretation that selects the preferred context is committed, any realist interpretation that selects the preferred context is committed to consider how that set is transformed under the Galilean group, because the Galilean group is the symmetry group of quantum mechanics. What means this? The preferred context, we suppose that the acquisition of definite values by observables is a real physical phenomenon. That phenomenon cannot depend on the perspective from which the system is described, cannot depend on the reference frame. This phenomenon should be invariant under the Galilean group. And this is something completely basic and reasonable. But if this is the case, which are those observables that are invariant under the Galilean group? Well, they are the Casimir operators and functions of the Casimir operators. So, in short, they should be Casimir operators. And which are the Casimir operators of the Galilean groups? Well, mass, square spin, and internal energy. Mass and square spin, well, they both commute with the Hamiltonian and do not break its symmetries trivially because they are multiples of the identity. Okay, but what happened with internal energy? So, I remember when we were thinking about this with Mario Castagnino, we say, oh, we have a problem. The Hamiltonian is not the internal energy, and it is the internal energy what should acquire a definite value. But if you think a little bit, the structure of the energy spectrum is really carried by the internal energy. But the Hamiltonian is the internal energy plus kinetic energy. And the kinetic energy, the only thing that makes is to translate the energy spectrum, a kind of well, an amount, yes. In fact, if we select for the description of the system the reference frame of the center of mass of the system, the internal energy is the Hamiltonian. So, okay, I mean, we should call our interpretation really Casimir model interpretation, because it would be more strict than Modal-Hamiltonian interpretation or Modal-Casimir interpretation instead of Modal-Hamiltonian interpretation. But it was late at that time, so we didn't change the name. But the fact is that the Hamiltonian rules, because it's also not only because it is the law, but because it carries the relevant part of the Casimir operator internal energy. So, which are the conclusions regarding invariance? Well, first, any realist interpretation that intends to preserve the objectivity of definite valuedness must make the selection of the preferred context Galilean invariant. If not, they would make a physical process to depend on the perspective. Therefore, it may not stand very far from the Modal-Hamiltonian interpretation, because these are the Casimir operators are the invariant, the invariant observables under the Galilean group. Second, that this view may give a general framework for interpretation. We can say in general for any theory, quantum theory, not only for quantum mechanics, that the definite value observables are the Casimir operators of the corresponding symmetry group, the symmetry group of the theory. For instance, in quantum mechanics, okay, we have mass, square spin, and internal energy. In relativistic quantum mechanics, we lose internal energy because it is assimilated to mass, so we have only two Casimir interpretation, Casimir operators, Casimir observables or operators, mass and square spin. And this is reasonable because elemental particles, we assume that they always have definite values of mass and spin. And furthermore, those values are precisely what define the different kinds of elemental particles. So to rely on the Casimir operators of the symmetry group is not something unreasonable, on the contrary. Well, and if we go to quantum electrodynamics, well, a charge appears. And why charge appears? Because we can say that the symmetry group, we can rely on the symmetry group of the theory, and the symmetry group not only is the space-time symmetry group, we can include internal gauge symmetries, and so to obtain charge. Well, I hope to have given some general reasons to make this interpretation at least reasonable. It is interesting that when one explains this to physicists from this viewpoint, so they say, oh yes, this is reasonable. I mean, because it's something that they can understand easily. They can understand the physics of the matter. Well, finally, let us say some points of about the difference between the two formalisms. Well, okay, we know that both formalisms are a mathematical equivalent. However, in the Hilbert space formalism, the system is represented by a Hilbert space. So the primary object, the primary elements are states, states of systems, states of particles, states that point to an individual system or particle. And observables are secondary elements applied to states. They are ontologically properties of those individual systems. What happened with the algebraic formalism? The system is represented by an algebra of observable, a star algebra or something more general if you want. Let us take a star algebra. The primary elements are the observables, are the properties, and the state is a secondary element. It's only an expectation value functional on the algebra of observables. It's something that applies to observables, so appears later, not first. I mean, logically, yes. When Ehrman talks about the algebraic formalist, he says, never forget the mantra of the algebraic formalism. A state is nothing else than an expectation value functional on the algebra of observable designed to compute expectation values. It's nothing else, nothing to do with properties. It's not a property. So the Hilbert space formalism suggests an ontology of individuals targeted by states and properties represented by observables. By contrast, the algebraic formalism suggests an ontology of properties, an ontology where properties are the basic elements of the ontology. So this is the door to the second part of the talk. Well, the ontology. I will begin with an intuitive very fast and intuitive approach. Then I will give a metaphysical picture, and I will say how this picture solves the ontological problems. Well, we have mathematics, physics, and ontology in this algebraic approach. I have self-adjoint operators that are physically observable, and the ontology, I have universal type properties with their instances. So an observable is an instance of an universal type property. An universal type property is energy, say, and an instance is the energy in this system. Yeah, like instances, universals and instances. The eigenvalues of the operators are values of the observables and are possible case properties. The difference between type properties and case properties is the difference in metaphysics between the terminable and the terminate properties. We will come back to this point. I use type and case, well, because I think that philosophers of physics do not know those kind of things of the history of metaphysics, but also because for me to say the terminable and the terminate is very difficult, type and case is very easy for me. So it's something that physicists understand better. A type property, for instance, is color, and case properties of color are red, green, yellow, etc. What happened with actual case properties? Among these possible case properties, no more than one, perhaps none, acquire an actual value. Well, this has no representation, no in mathematics, no in physics. Now, the system that is mathematically represented by an algebra of operator, ontologically is a bundle of those instances of universal type properties. The probability is a propensity. I will not talk a lot about this. I have a realist propensivistic interpretation. And the state is codification of propensities. And my idea is to write a paper discussing more deeply on this matter, but it's not ready already. It's not ready yet. So let us begin with the intuitive approach, very intuitive. Let us suppose that we have a system. The system is a bundle of properties, but it's non-individual item. Let us suppose that, well, you see in red the values of the observable A, in blue B, and so on. Why I say that it is non-individual? Because it has no principle of individuality. I mean, an individual is something that has synchronic identity and diachronic identity. Synchronic identity is what makes this individual, that one, different from all others. And diachronic identity is what makes that individual the same over time. Well, we have nothing at all in quantum systems. So we can talk about bundles, but not in the sense of the traditional bundle theory of metaphysics, of metaphysics, if you want, from Hume, but with this name, bundle theory in the 20th century. In the traditional bundle theory, the idea is that the bundle has to recover the idea of individual. So one has to find some property who gives the synchronic and the diachronic identity. Here, the bundle is not an individual, so we don't need a principle of individuality. And this explains what? This explains that when we combine two systems, for instance, these two, we obtain another system. But this system now is a new bundle, completely a new bundle, where the original bundles cannot be re-identified. I mean, we have not two little particles, balls, that can be re-identified when I put them together. Now I have two bundles, and when they are put together, they make a new bundle, so the original bundles are lost in the new bundle. And what means that? This has a very relevant consequence for indistinguishability. Because let us suppose that we have two indistinguishable bundles, like these two, yeah? And now I want to combine them. I also obtain a new bundle, and this bundle also is unique, sorry. But the relevant feature of this new unique bundle is that it's symmetric, because of composed of indistinguishable bundles. This means that indistinguishability, that originally thought as a relationship between particles, now is a symmetric property of a single composite system, that is a new composite bundle, a new bundle. Well, this was very intuitive. Let us see from a more serious, if you want, metaphysical viewpoint. Well, we have universal properties and instances of these universal properties. Universal properties may be type properties. I use a kind of terminology to distinguish them, which have universal case properties. Yeah, I mean, energy may have different values of energy from a completely general viewpoint. Nevertheless, they can be, the universal type properties can be instantiated in a singular system that is not an individual, but it is this system. We have a problem with our language to say this, because our language is modeled on individual properties metaphysics. These type properties, that are instances, also have instances of case properties when specified in a single system. So a bundle is a collection, we will say something more, it's a quasi-set of I-type properties. Yeah. Why a quasi-set? Well, I will say this later. Quasi-set because, well, now, a bundle cannot be a set, because set theory is designed in terms of the elements of a set are individuals. The theory is designed to talk about individuals. In the traditional bundle theory, there is no problem, because this was designed to account for individuals. This bundle theory dispenses completely with the ontological category of individual, so bundles do not behave as individual at all, and they belong to a different ontological category. And if this is the case, I cannot use, I have no individuals at all, so I cannot use set theory. So we are using quasi-set theory. Last year appeared a paper with two person of my group, and Decio Kraus, our friend Decio Kraus, who is the author of quasi-set theory, applying quasi-set theory to this case. It's an application completely different to that devised by him originally, but it's an interesting application new application of a quasi-set theory that, of course, can be applied in different ways because it is a formal theory, so it has not an only a single application. Well, given two bundles, the composition of bundles is a new bundle, trivially formed like that, and given I-case properties, they are indistinguishable where they are instances of the same U-case property. So we can talk about indistinguishable I-case properties. For instance, if I say red, I mean a specific value of red here or red there, they are completely indistinguishable. Properties in their different instances are not distinguishable. Making distinguishability, applying distinguishability to individuals is a problem, but to properties is something natural, if one to say this simply. Given type properties that are indistinguishable, given two I-type properties, they are indistinguishable when they are instances of the same universal. Of course, they need to be instances of the same universal, and their case properties are indistinguishable from each other. Indistinguishability that was defined originally, first defined. And given two atomic bundles, well, is something that these are bundles that are represented by reducible representations of the Galilean group. They can be formally defined. Well, atomic bundles, they are indistinguishable when they are properties, the I-type properties that compose them are indistinguishable from each other. So, summing up, what we make is this. We began with the indistinguishability of I-case properties. That is something natural. Red and red are indistinguishable. This allows us to define the indistinguishability of I-type properties. And once I have the indistinguishability of I-type properties, then I can go to the indistinguishability of the bundles. But the indistinguishability of the bundles is derived from a property that in the basis is in the level of properties. And it's reasonable because properties are the fundamental elements of the ontology. Well, how to cope with these deontological problems? I say I will talk about three ontological challenges: contextuality, non-separability, and indistinguishability. Contextuality is a challenge for the principle of omnimote determination. Now, here the principle of locality, and here the principle of identity of indiscernibilities. Let us see each one. What the principle of omnimote determination says, this thing that belongs to traditional metaphysics. Quod libet existent est tot nimote determinatum. This means that every determinable is determinate. I mean, if an object has a determinable case property, for instance, color, it must have a determinated, a case property. It must have some color. It is colored. It must have some color, red, green, someone. I don't know which, but it must have one. It is something that appears in Kant, appears in Wolff, so it's it's traditional in metaphysics. It's all something that seems to be obvious if we know. But this could leave it, this something is an individual or a substance in the sense of Aristotle. But the problem is that here does not apply. I mean, we know that the contextuality challenged this because a system has certain properties, case properties, determinables that are not determinate. I mean, you can have a position that is determinate, but momentum, we know that it is not determinate. So this violates this, and it's not that we don't know that by Coach and Speckers we know that this is not determinate. So this principle does not apply. Why? Because quantum systems are not individuals, are not objects with properties, but mere bundles of properties. It is important to say, because some people say, they say that the principle is false, that the principle of identity of indistinguishable is false. No, it's not false, does not apply, it's different. The principle of locality, well, one may say that correlation between systems are due to non-instantaneous interaction. There are not interactions that travel instantaneously, or as Einstein said, the identity of physical system is given by their space-time position. He said, if this is not the case, I don't know what physics is, if you remember that quote. But when they are thinking in systems, they are thinking in individuals. Again, this principle of locality does not apply. Bundles are not individuals. They cannot be re-identified in the composite bundle. So there are no correlations between two systems that travel instantaneously. There are no correlation between two systems, but not because they don't travel, because there are no two systems. What we have is internal correlations within a single system, and correlations between properties of a single system is something completely natural. Anything, classically even, has correlation between his length and his height and his area. Well, this is completely natural. The problem is when we have two systems, two individuals placed at different positions at a certain time. And what about indistinguishability? The principle of identity of indistinguishability says that if two objects have the same properties, they are the same object. I mean, X and Y are only names, different names of the same object, of the same individual. So again, we are talking about individuals, and again, the principle of identity of indiscernibles does not apply, because indistinguishability is not a relationship between particles or objects or individuals, but an internal energy, an internal symmetry of a composite bundle. I talked with Gonzalo Pereira. He's Argentine. He's a very good, well, I think that is perhaps the specialist in the principle of identity of indiscernible international level. And I was discussing with him, and he said me, yes, if this were the case, it does not apply. The problem was that he never could understand why I wanted to reject individuals, because he couldn't understand really the problem of indistinguishability in quantum mechanics. But if I reject individuals in my ontology, okay, so the principle does not apply. It's not false, again, it's not false, does not apply. Well, the third part, very fast, I will revisit indistinguishability from this viewpoint for who like formal things, physical presentation, because it was very intuitive and metaphysical. Well, what happened with symmetric observables? Well, systems are bundles. Let us suppose that we talk about two bundles and represented by two algebras. And the aggregate of bundles is a new bundle whose elements are have this form. Okay, who likes formalism can understand that it's a superposition of tensor products of the observables of the two algebras. When I apply this aggregation on indistinguishable bundles, the two components algebra are indistinguishables, so they are only numerically different. This means that when I take these two bundles to merge into a single whole, which component I take first and which second does not matter. It's completely irrelevant. This means that that bundle aggregation of indistinguishable bundles must be commutative. I mean, any observable of the new bundle, any observable made in this way when the component bundles are indistinguishable, must be represented by a symmetric operator respect to the permutation of the indices coming from the two original algebra. Because which algebra I takes first and which second does not matter at all. And this is manifested by the fact that the operator must be symmetric. So again, distinguishability is no longer a relationship between individual particles, but an internal symmetry of a whole closed system, in particular, an internal symmetry of the observables of the composite system, the whole composite system. But what happened with symmetric states? Because we are used to symmetricize, anti-symmetricize states. Well, let us consider not states as from a general viewpoint, not vectors, but density operators. Let us suppose that we have a density operator, yeah, a state. Any matrix, if you want, has a symmetric part and anti-symmetric part. Yes, a symmetric part as the components are like this, and the anti-symmetric part are like this. This is what symmetric and anti-symmetric matrix means or operator means. The fact is that if I take a symmetric operator and I make the expectation value in a state, I have to make the trace of rho by O, the symmetric O. This rho has the symmetric plus the anti-symmetric part, but it is known that the trace of an anti-symmetric operator by a symmetric operator is 0. So we remain also with the symmetric part of the state. The symmetric part of the state, I mean, this symmetric state is, I mean, the expectation value of the symmetric observable in the symmetric part of the state. Of course, the symmetric density operator can come from symmetric vector or anti-symmetric vector. In both cases, I obtain a symmetric density operator. The fact is that the antisymmetric part of the state has no effect in its application onto symmetric observables to compute expectation values. That is the only role of states. Let us remember that. From an algebraic viewpoint, the only role of the state is to compute expectation values. So the symmetry of the operator representing physical states of aggregates of elemental particles is not a result of an ad hoc symmetrization on states or on observables, but is due to an ontological reason. That is due to the very structure of the ontology. We have an ontological justification for symmetry. Well, what happened with indistinguishable? See,
I'm sorry.
5 minutes or
5
less.
minutes.
Yes,
Perfect.
or less.
Perfect. I'm sorry.
No,
then.
I think that less. The indistinguishable principle can be expressed normally that for any composite system whose components are indistinguishable particles, the expectation value of any observable must be the same for the state and for the permutation of the state. This is something traditional. Nevertheless, it can be also expressed in terms of symmetric observables. For any observables of a composite system whose components are indistinguishable subsystems, its expectation value in any state must be the same for that observable and for the permutation of that observable. In this is the, well, Van Frassen emphasizes that even if mathematically are equivalent, these are not equivalent from the interpretive viewpoint. Here we are talking about states, and here we are talking about observables, and it establishes a restriction on states, and this establishes a restriction on the observables. This appears also in a very old paper, so it's not, I'm not inventing this. So it is clear that from our viewpoint, this is the formulation of the distinguishability principle that matters. And this has a final advantage regarding the symmetry of the Hamiltonian. According to the traditional argument, the bosons cannot be transformed into fermions, so the parity of the permutation operator must be invariant and constant of motion, so it has to commute with Hamiltonian, and so the Hamiltonian must be a symmetric observable. Well, the symmetry of the observable must be added to the symmetry and anti-symmetry of the states. By contrast, if we work with symmetric observables, the symmetric observables that are commute with the permutation, well, the symmetric and anti-symmetric states are also eigenstate of P. Well, they are also eigenstate of the symmetric observable, but the fact is that any observable or any symmetric observable also preserves the symmetry and the antisymmetry of states. It means that any observable that is symmetric makes bosons, fermions, do not transform boson into fermions. And the Hamiltonian is one of those symmetric observables, so bosons cannot be transformed into fermions and vice versa. And I will say this very short. If all the observables of the composite system are symmetric, the Hamiltonian is one of them, and it has to be symmetric too. So I have not to include it as an ad hoc. So if from the viewpoint of this formulation of the indistinguishability principle, that establishes a restriction of states, the symmetry of the Hamiltonian must be posited as an additional condition. From this view, that establishes a restriction of observables, since all the observables must be symmetric, the symmetry of the Hamiltonian follows directly from the principle and is not necessarily a further requirement. So, thank you.
Thank you to you, Olimpia. Was very, very interesting and very detailed. So it's been a real pleasure to listen to this very, very interesting presentation.